Welcome to the Deep Dive. Today we're tackling a huge topic, artificial general intelligence, AGI. Now, you hear AI thrown around constantly, right? Chatbots, image generators, they're amazing, no doubt. But we're going deeper today, beyond that kind of narrow AI, into the much bigger, much trickier idea of truly general human-like intelligence. And we're basing this on a collection of really insightful perspectives from experts, all pulled from a book called Artificial General Intelligence. These aren't just quick takes. They're pretty deep dives into the theory and the actual practice from people right at the cutting edge.
Right. And our goal here, our mission, is really to pull out the key ideas from these sources. We'll look at how people even define intelligence in this AGI context, which is surprisingly varied. We'll explore the different paths researchers are trying, the different ways they think we might actually build AGI, and crucially, the big challenges they're running into. The idea is to give you some clarity, some context that goes beyond the headlines, maybe even challenge how you think about it.
Okay, so let's dive in. The most basic question, but maybe the hardest. What is intelligence anyway? I mean, the dictionary gives us something like capacity to acquire and apply knowledge, faculty of thought and reason. Seems simple enough on the surface. But in AGI, especially looking at our sources, it gets way more complex, doesn't it?
Oh, absolutely. It gets much, much more nuanced. Take Pei Wang's definition. He really focuses on something often missed: the system's ability to adapt to new knowledge, and not just adapt, but adjust its own memory, its own structure to get better, more efficient, assuming the future will kind of resemble the past. And here's the really interesting bit. He contrasts this with systems that assume, like, infinite computing power, like Marcus Hutter's AI-XI. Wang argues that needing infinite resources might actually be unintelligent, because intelligence is about working with limits.
Wait, so infinite power is unintelligent? That's counterintuitive.
Exactly. Because for Wang, an unintelligent system is one built assuming it always has enough knowledge and resources for the problem at hand. A truly intelligent system, he argues, is one that figures things out even with insufficient knowledge and resources. It's about adapting to scarcity and uncertainty, making smart choices when you don't have everything.
Okay, I think I'm getting that. So, systems that learn and adapt when things are messy and incomplete. How is that fundamentally different from the narrow AI we use now? Like the chatbots, the image tools, they learn from data, they seem to adapt.
That's a really important question. And it's easy to get confused there. A lot of the current narrow AI work, it kind of assumes that if you solve enough small, isolated problems, you'll eventually get to general AI. But cognitive theory and just practical experience suggests it might not work that way. You see, the best way to solve one specific little problem might be totally wrong for how that function needs to work inside a truly general system, one that has to juggle tons of different things coherently.
I see. So it's not like Lego bricks you just click together.
Not necessarily, no. Building super specialized tools isn't the same as building an integrated mind.
Right, that makes sense. So if just stacking narrow AIs isn't the path, what are some of the big ideas for actually achieving that integration, that, unified intelligence?
Well, one major approach is called the integrative approach. This is where you try to combine ideas and techniques from different AI fields into one system that works together, synergistically. Think of projects like Novamente. But the catch is, you can't just bolt these different parts on. Often, the ideas themselves have to be kind of reinvented or adapted so they fit into a single unified framework for knowledge and how the system thinks and learns. They need a common ground.
Okay, so you're not just plugging modules together, you're rebuilding the parts so they actually mesh properly. That sounds hard.
It is definitely a major challenge. Getting different philosophies of AI to speak the same internal language, yeah, that's tough.
What about other approaches? People always talk about, just copying the human brain. Seems like the obvious route.
It does seem obvious, right? But the sources are pretty clear that this is maybe deceptive. Simulating a whole brain, incredibly complex. And even things like neural networks. Most of that research isn't about simulating actual neurons one-to-one. It's more like neurally inspired modeling, using brain ideas for cognitive processes.
Oh.
And here's a key point from the sources. Even if you did build a perfect brain simulation, it might be a huge win for neuroscience, telling us how our brains work, but not necessarily a win for AGI itself. The goal for AI is intelligence, right?
Yeah.
Not necessarily making a perfect biological copy. The how might be very different.
Okay, fair enough. So perfect brain copy, maybe not the direct path to AGI. What about copying human behavior? The Turing test, that whole thing?
Yeah, the Turing test comes up a lot, but the sources point out something interesting. To really pass it convincingly, long term, a system wouldn't just need to think like a human, it would need a lot of prior human experience.
Yeah.
Which implies Having a body that feels human-like, having human motivations, being treated by others as human. It starts to sound less like building a smart computer and more like building an artificial human.
Wow. Yeah, that does sound like a different goal almost. An artificial human. Does that change what we even mean by AGI? Are we trying to replicate us, warts and all, or just build something intelligent? It seems like it opens up a whole other can of worms. Okay, let's shift gears a bit. If biology and behavior have these complications, what about pure logic? Foundational, abstract approaches?
Logical approaches are definitely a big part of the picture. Systems like NARS or Novamente, again, use something called term logic. It's a bit different from the predicate logic maybe more people know. Predicate logic is often about relationships between individuals. Socrates is a man. Term logic often focuses more on relationships between concepts or classes. All men are mortal. It structures knowledge differently. And crucially for AGI, these systems need to handle uncertainty. They don't just work with true-false. They use things like fuzzy truth values, degrees of certainty. So instead of just true, it might be probably true or somewhat uncertain, which is vital for the real world because, let's face it, things are rarely black and white, right?
That makes total sense. Real world is messy. Okay, and I read something interesting about a neural net approach that doesn't need a physical body.
Ah, yes, you're probably thinking of Peter Voss's A2I2 architecture. It's a neural network approach, but it's designed holistically for AGI from the start. It uses different kinds of reinforcement learning, all working on a common network structure. Now, it has some similarities in spirit to embodied AI work, like Rodney Brooks's COG project, learning through interaction. But Voss's view is that the physical body isn't strictly necessary. He thinks you can get that essential experience-based learning, even if the system's inputs and outputs are purely virtual. It can experience a simulated world.
Interesting. So experience matters, but maybe not physical embodiment per se. But then intelligence isn't purely individual either, is it? We learn things socially.
Exactly. That's a really critical point raised in the sources. Traditionally, AI often thinks of a mind in one computer. But social psychology tells us our minds are deeply shaped by being in social groups, cultural contexts. So one AGI idea is build individual AGIs, then let them interact. Maybe they even develop their own language, like in the Novamente project. Another way is to design the systems to be inherently social from the ground up, build communication, cooperation right into their core architecture. And related to that, there's the animate approach coming out of artificial life research. This uses biologically inspired robots, either simulated or real, that learn by interacting with their environment and maybe other agents. The argument here is that you need that embodiment, that interaction with a physical world, to ground intelligence, to learn about cause and effect, physics, being in a world.
Okay, so we have mimicking brains, behavior, logic, virtual experience, social interaction, physical interaction. Lots of angles. What about a more fundamental view? Like intelligence is basically just about finding solutions, a search process.
Yeah, that's the idea behind program search as a path to AGI. The core idea is framing intelligence as a search. Not just searching for answers, but searching for programs that have certain abilities. And crucially, programs that can even search for better versions of themselves that optimize their own structure. Jürgen Schmidhuber's work on Gödel machines is a really fascinating example here. These are theoretical systems designed to be fully self-referential, optimal, universal self-improvers. Think about that. A program that can examine its own code, prove that a change would make it better according to some goal, and then rewrite itself to become better. Learning how to learn, essentially. And importantly, these are often conceived to work with realistic computational limits. Unlike something like AIXI, which often needs, well, practically infinite resources.
It's a program that rewrites itself to get smarter.
Wow, okay. How about going even more fundamental, like back to biology and evolution? Vladimir Redko makes that case. He argues for modeling evolutionary processes as a scientific foundation for AI. Use a great example, Pavlov's dog. The dog infers food is coming when it hears the bell. That's basically logical inference, modus ponens. If bell A, then food B, bell A happens, therefore food B. He argues this shows how even basic logic has evolutionary roots tied to survival. His own computer models, like one called the Model of Evolutionary Emergence of Purposeful Adaptive Behavior, focus on simulating agents driven by basic motivations. Food, mating, and seeing how intelligent behaviors might emerge from those evolutionary pressures.
Interesting. So intelligence isn't just dropped from the sky, it evolved from basic needs. Okay, one more major idea, this one sounds pretty complex, but the structure of mind, layers of thinking.
Right, that brings us to Eliezer Yudkowsky's Designed General Intelligence, DGI. He puts a lot of emphasis on levels of organization in deliberation, how thinking is structured.
He argues human intelligence isn't flat. It's built in layers. You start with neurons, then you get sensory processing, then concepts, then thoughts, then beliefs. Concepts, for instance, aren't simple labels. They have complex kernels for matching patterns, like recognizing the abstract idea of fiveness, whether it's 5 apples or 5 fingers. Thoughts are like combinations of concepts that play out in a mental imagery, which he sees as an active workspace, a canvas for thinking things through. And he even talks about questions being like thought magnets, pulling deliberation in a certain direction, and goals being action magnets. It's a very architectural view of how a mind might be constructed.
That's a lot of different approaches. Brains, logic, search, evolution, architecture. But reading through these sources, one thing really stands out. They're quite blunt that none of these pathways have actually, proved itself successful yet. They even say researchers' gut feelings about their own projects are highly chancy.
Yeah.
That's pretty sobering, actually, after hearing all these cool ideas. What does that tell us?
Yeah, that honesty is important, I think. It tells us AGI is still very much a research frontier. One big warning from the sources is to avoid physics envy.
Physics envy, what's that?
It's the temptation, especially in a complex field like AI, to look for one single elegant underlying principle that explains everything about intelligence, like physicists seek fundamental laws. But human intelligence, the sources argue, is probably not like that. It's enormous, complex, and likely emerged from many different parts working together, synergy, not singularity. It's messy. And there's another deep challenge, the difference between our brains and computers. Brains are relatively slow at the component level, but massively parallel. They're smooth and stochastic, good with fuzziness, probability, our programs. Super fast, but often sharp and fragile, crystalline. They break easily if conditions aren't exactly right. So AI development has to actively figure out how to build robustness, that kind of smooth adaptation into these very different non-biological systems. It doesn't come for free like it might in a brain.
Physics envy. I like that phrase. It really captures that desire for a simple answer to a complex thing. Okay, so given all these challenges, the messiness, the substrate differences, what's maybe some counterintuitive advice for developers?
One of the most interesting bits of advice is about knowing what not to program.
What not to program.
Yeah. Instead of trying to foresee every possibility and hard code every bit of knowledge or every function, the emphasis should be on building systems that can learn autonomously. Systems that can adapt when things change, that can figure stuff out for themselves. Using techniques like fuzzy pattern matching helps them be less brittle, more robust when they encounter something unexpected. It's about giving the system the tools to learn and adapt, not trying to pre-program the entire universe into it.
Right, build the learning capability, not just the knowledge database. Okay, so wrapping this up, what's the big picture for our listeners? What should they take away from this deep dive into AGI?
Well, I think the key takeaway is that AGI isn't just about making today's AI faster or bigger. It's fundamentally different. It's about systems that can learn across many domains, adapt to novelty, handle incomplete information, manage limited resources, maybe even be creative or unpredictable, hopefully in ways that benefit us. It's really a shift from specialized tools towards potentially general adaptable artificial minds.
And hopefully this discussion gives you a sense of the sheer variety of ideas out there. We really encourage you to look into these different approaches, think about their pros and cons. It's clear AGI is this incredibly active, vibrant research area, lots of exciting ideas, lots of projects, but the big questions, they're definitely still wide open. And maybe a final thought to leave you with. Human intelligence is kind of messy, right? It evolved over time, lots of specialized bits cobbled together. It's recent, evolutionarily speaking. So if we manage to build AGI through deliberate, careful engineering, will that intelligence actually look like ours? Or will its planned, coherent design result in something, well, fundamentally different, maybe even something we call transhuman, something to think about?